Good day to everyone. I am Kapil from Midas, Singapore, and I welcome you all to this webinar. The topic of today's webinar is design of Super T girder bridges as per AS5100. Today, our discussion will be focusing on the design of Super T girders, including the creep and shrinkage models as per the new code. Super T girder bridges are the most common bridge types in Australia and New Zealand, and today we will discuss some of the modeling techniques that can increase the efficiency of design of Super T bridges. The duration of the presentation as well as the demonstration will be around 40 to 45 minutes. If you have any questions in the middle of the presentation, then you can write down the questions in the questions window. Some of you might be new to Midas Civil. Therefore, before beginning my presentation, I will just give you a brief introduction about the program. Midas Civil is a 3D FEM software for bridge and civil structures. The interface of the software has been optimized for the bridge structures. Midas Civil can handle from the simple static analysis to the advanced analysis, such as construction stage analysis, linear and nonlinear dynamic analysis, and so on. Midas Civil can handle the conventional bridges like the frame and the box culvert bridges, and it can even handle the segmental bridges, and advanced bridges like cable stayed and suspension bridges can also be taken care in Midas Civil. Today we will discuss specifically about PSC composite bridges and focusing on the Super T type of bridges. Today we are going to model this particular bridge. This is a 3-span bridge and the span length is indicated in the figure. The first and the third span of the bridge are 32.24 meters and the mid span is 36 meters. The pier height is also known to us, and the next figure shows the detailed plan of the bridge. We will first start with a 3-span bridge. Then we will extend the application of the program to the 7-span bridge. This figure explains the bridge section in the transverse direction. The deck is 180 mm thick and there are 6 Super T girders in the bridge. The pier column is 120 mm diameter and it is circular in shape. It is also shown in the figure. And there are 2 precast concrete barriers on each edge of the bridge. So here we have 2 precast concrete barriers. Looking more about the bridge section, we can see that there are 4 lanes on the bridge. So we have lane 1, lane 2, lane 3 and lane 4. And width of each lane is 3.5 meters. Then there are 2 shoulders, each of width 1.28 meters on each side. Then the width of the precast concrete barriers is 600 mm. In the next figure, we can see the headstock. We can see the details of the headstock in this figure. In order to help you understand the bridge section in details, the modeling statement was already sent with the invitation email. So we will be discussing about the modeling of this bridge. We will take into account the creep and the shrinkage as per AS5100 part 5, and we will discuss about the clauses of AS5100 part 5 2016. It is expected to be released towards the mid of this year. So we will use that particular code. Now we will talk about the material properties used for the various elements in the bridge. Superstructure of the bridge is of 50 MPa and we will take into account the creep and the shrinkage model as per the draft of AS5100 Part 5, and the development of concrete strength with the time, it will be taken care as per the same code. Then we have the information about the pre-stressing strands. So the strand diameter is 15.7 mm and the yield strength and the pre-stressing force is also mentioned on this slide. We will be using the low relaxation strand for our model today, and we will calculate the relaxation loss as per AS5100. Now talking about the section properties, we will use the Super T girders. Since the maximum span length is 36 meters, so we can choose the depth of the Super T girder accordingly. We can choose the Super T girder to be 1500 mm or 1800 mm deep. It is upon us to decide what depth of the Super T girder that we want to use. In this model, in today's example, we will be using 1500 mm deep Super T girder, and the pier will be 1.2 meter in diameter, and the details of the pier cap as well as the diaphragm section are also mentioned. Pier cap is commonly known as headstock. So the section properties of headstock as well as diaphragm are also mentioned. Now this is the tendon arrangement for 1500 mm deep Super T girder. So here let us have a look at the tendon arrangements in detail. There are 5 rows of tendons, and debond length of each strand is also mentioned in the table. So we will see that how we can incorporate this debonding effect in our model, how we can quickly incorporate the respective details in the Midas civil model. Then we need to calculate the relaxation loss as per AS5100 Part 5. The relaxation model of the new code is essentially based on CEB-FIP model of creep and shrinkage. The formulas used in the relaxation loss are mentioned in this slide. Now let us begin the modeling of the Super T girder bridge. Midas Civil is a general purpose 3D FEM software, so we can model the bridge using the conventional method of nodes and elements. User-friendly GUI of the software provides a lot of options in order to model the bridge quickly and with every minute details. Then the other option that we have for Super T bridges is the PC Composite Bridge Wizard. In 5 simple steps, we can model every shape of the Super T bridge. Even if it is a curved or a skewed bridge, we can easily model each and every shape of the Super T bridge using this bridge wizard using 5 simple steps. So for today's presentation, we will be using this bridge wizard in order to model the Super T bridge. As I mentioned that this bridge wizard can be applied to various curved bridges, skewed bridges, multi-curved bridges, and varying super elevation as well. So let us see what this wizard is about. The bridge wizard can be found in the structures tab of the program. So if you go to the structure tab, then in the structure tab, you will find PC composite bridge wizard. And in the wizard, we have 5 tabs: layout, section, tendon, load, and construction stage. So we will see that how we can play with these 5 tabs and we can model any shape of the bridge. We will see the details of each tab in a few minutes in the demonstration part. I will email this presentation to everyone after the completion of the webinar. You can refer to it for your learning purposes. If you need to check more details about the wizards, then you can refer to the links provided here. So These are the links for the online manual of Midas Civil. And if you click any of the links, then it will take you directly to the online manual. For example, if you want to see about the details of the layout tab, then you can just simply click this button and it will open the layout tab in your browser. So here you can see that as I clicked the layout tab, the program is opening the layout tab in a web browser, and you can see all the details of the layout tab here. So for your convenience, I have provided the links for all the 5 tabs here. So when I will send you the presentation, you can refer to this presentation and you can use these links to learn about more details of each tab. So in the Bridge Wizard, first we will see about the layout tab. So in the layout tab, you can see that you can specify about the girder type, if it is a precast girder or it is a splice girder bridge. Then you can see about the modeling type. So you can choose the entire bridge to be modeled as all frame, or you can choose the entire model to be modeled as the girder as frame and deck as plate. Then you can input the bridge dimensions. So you can input the span length, you can input the curvature, and you can input the girder alignment options. And along with that, you can even specify the substructure. So you can specify if you want to model the substructure without it, and if you want to model it without the substructure, and the program will automatically generate the headstock or the pier cap, and it will generate the piers for you, and all the elastic links and bearings, they will automatically be generated. Then we have the section tab. In the section tab, we can specify the thickness of the deck. This thickness of the deck will be used to generate the transverse elements of the bridge. Then in the materials tab, you can specify the thickness of the material. You can specify the material for each and every part of the bridge. Then you can specify the number of girders, and you can specify the offset for the girders from the centroid of the bridge or from the reference line of the bridge. Then you can specify the diaphragm sections, and you can specify the girder information. Then we have the tendon tab. You can specify the various arrangement of the tendons. You can specify the debonding length in one Excel sheet. And then you can specify the load. The program will automatically apply the load of the precast barriers. And if there is any median strip, the program will apply the load of the median strip for you as well. And we will be able to see the construction stage as well. The construction sequence for a Super T bridge generally includes 4 steps. The first step is that the open Super T fabricated in factory, and then it is transported to the construction site. The second step is that the Super T girder is lifted and it is secured on the top of the substructure, that is abutments and piers. The third step is that we set up the sacrifice or the formwork, and we lay out the deck reinforcement and cast the concrete deck. And the fourth step is that the concrete deck hardens and it composites with the precast Super T. So this entire construction sequence will be generated by the wizard itself. So this is the bridge that we will start to use. And in order to see the details, let us go to the program directly. So here I have a model file in which there is no information about the bridge yet. So we will create the entire information of the bridge in this model. So here in the worksheet on the right hand side of the screen, you can see that what information is already defined in the model. We will review this information and then we will start modeling the bridge. So first information is the material properties. We have created the material for the superstructure. We have created the 50 grade concrete and we have created the materials for the strands. So we are using 15.7 mm strands and we have created the material for the same. Then we have generated the time dependent material properties of creep and shrinkage. So here let us review that what time dependent material properties we have used. So here we can see that we have generated the time dependent material properties for 50 megapascal concrete. For your convenience, I will change the units. For now, I will change the units to Newton and mm. So here you can see that the compressive strength of concrete at 28 days is 50 megapascals. And in order to calculate the final drying basic shrinkage, we have chosen the particular exposure environment. Then we have provided the hypothetical thickness, and then we have mentioned the age of the concrete. So here you can see that we can see the creep curve as well as we can see the shrinkage strain. We can see the curve in the form of a graph, and we can even see the values in the form of an Excel for both creep as well as shrinkage. And if we want to see the creep curve for a different loading age, we can just change the loading age here and the program will redraw the creep curve for you. So this creep curve is as per AS5100 part 5, and this creep curve is as per the draft version. This creep curve can also be applied to the New Zealand bridges, and we just need to change two factors. We just need to change the location and the exposure environment. So based on that, the program will generate the creep curve for the New Zealand as well. And then we have the development of compressive strength with time. For the development of compressive strength with time, we have a model as per AS5100 part 5. And once you input the concrete compressive strength, the program will generate the gain of the compressive strength with time. Then we have the relaxation function. So this relaxation function is AS5100 part 5 and it is low relaxation strand. So these values have been calculated and provided, and we can use this for the modeling and analysis of our bridge. Then the next part comes is the Super T section. So the program has a Super T section database for Australia as well as New Zealand. So for example, if you want to use the Super T section as per Australian standards, then you can choose that if you want to use the 1800 mm deep Super T section, 1500 mm deep Super T section, 1200, 1000 and 750 mm depths are available. Along with that, the other sections available as per the Australian standards are eye girders. So you can choose the eye girders as per the Australian standards. And for New Zealand, there are two eye girders available for the database, and the Super T sections, the depth of the available sections for the New Zealand standard is 1025 mm, 1225 mm and 1225 mm. Depending upon the span length, the shape of the Super T section is changing. So all the database is available in Midas Civil. So here we will see the Super T section. So this is the current Super T section that we are using. And if we need to change the top flange width, then we can easily change the top flange width for the Super T section here. And we can use the Super T section with the different flange width. So here you can see that we can easily change the flange width of the top flange, and the program will use that particular flange width, and we can start the analysis and design. So here for the Super T section, we actually have the width of the top flange as 2.96 meters, and above that the thickness of the deck is 180 mm, and we have specified various results. And if you want to see the section properties, you can refer to the section properties before the composite action as well as after the composite action. Both the values are available in the table form in Midas Civil. Then we have the section for the pier column. So it is 1200 mm in diameter. And we have the section for the headstock or the pier cap, and we have the diaphragm section. And then for the tendon property, we have specified the tendon to be 15.7 mm strand, and the duct diameter is provided accordingly. And the various losses will be calculated as per the provided values. Now let us start the modeling of the bridge itself. Let us proceed step by step. So here you can see that there is no node or no element currently in the model. So we will go to the pre-stressed composite bridge wizard. Just to save the time, I've already provided the information about the various parameters. So we will review the entire information. So here you can see that the girder type is a precast girder type, and for the span information, we have provided the spans of 32.24 meters, 36 meters, and 32.24 meters. If we want to change this data, we can simply change this data. And now you can see that the span information is 32.24 meters. Then there are 5 spans of 36 meters. Then there is the last span of 32.24 meters. So we can easily change the span information here. And we have provided the deck width of 17.76 meters. And the spacing between the two girders. So here you can see the figure that the spacing A is the spacing between the two girders. So it is 150 mm, and the spacing between the edge of the girder to the center of the bearing is 250 mm. So we have provided the respective information here. And if you want a curved bridge, then you can specify the radius here, and the program will model a curved bridge for you. And if it is a skewed bridge, you can provide the skew angle here, and the program will model the skew bridge for you. So in this way, we can model each and every type of the shape. And here we can specify if we want the bridge to be with substructure or without substructure. So we can refer to the guide here. So here you can see that if we want to model the substructure, then we need to specify the bearing type and the stiffness of the elastic links. And we have specified the elastic length, which will be equal to the height of the bearings. And then we have specified the abutment, that we want to model a compression only supports for the abutments, or we want to model the fixed supports for the abutment. So both the options are available. And we have specified the stiffness of the elastic link, which will be representing the bearing. Then for the piers, we have specified the material, that the columns or the piers are of this particular material, and we have specified the section for the headstock, and we have specified the length of the headstock, and specified the section of the pier and the height of each pier and the spacing between the two piers. Now here, sometimes the case occurs that height of each pier is different. So what we can do is we can check on the advanced option, and here we can enter the height of each pier. Using this, the program is going to model the pier of that particular height for each and every section. And if even in our model we have more than 2 piers for one headstock, then we can simply provide the spacing of those piers. So for example, earlier the data was 11. So now the program will model 2 piers at a spacing of 11 meters, but let us say I change the spacing to 5.5 and 6. Then the program will model 3 piers. The first two set of piers will have a spacing of 5 meters, then second and third pier will have a spacing of 6 meters. So in this way we can provide the entire data. And for the support at the base of the pier, we can choose the support to be fixed, or we can choose the support to be spring support. And if it is a spring support, we can provide the stiffness values. Now talking about the section, we have to specify the section for our model. So the thickness of the deck is 180 mm. This thickness will be used to generate the transverse elements. And then we have specified the number of girders. We have 6 girders, and with reference to the center of the bridge, we have specified the offset for each girder. So we have specified this. And if you want to see the details, if you want to understand the parameters, you can click on the guide button. And here you can see that with respect to the reference line, we have provided the layout offset. And we have specified the diaphragm sections. So you can see the diaphragm sections are provided here. So this end support diaphragm represents these diaphragms, and pier support represents these diaphragm, and intermediate represents these diaphragms. So here you can see in the guide that what these parameters stand for. And then we have provided the girder information. So here you can see that in the first span for the first 2 meters, we have used a solid super T girder. So if you want to see, you can even see the girder properties. So here you can see that it is a solid super T girder and there is no void in it. And for the length from 2 meters to 32 meters, the girder is an open girder, and this is the particular type of super T girder that we are using for this span. And for the middle span, we are using the open girder throughout. And for the last span, for the first 30 meters, we are using the open girder, and for the last 2 meters, we are using the closed girder or the solid girder. So for the last 2 meters, we are using the solid girder without any void. And then I have to specify the tendon data. So let us see how easily we can specify the tendon data. I will just take you through the tendon information that we were expected to provide. So this is the tendon information that we want to provide to our bridge. So we have 5 rows of the tendons, and we have debonding length, which we should specify in the bridge. So here you can see that we have specified for the first span, we have specified the 5 rows of the tendons. So in the first row, we have 2 tendons at a distance of 660 mm. And if you want to see the detail, you can even refer to the detailed figure here. And then in the next row, we have 12 strands. We have specified the 12 strands here. In the figure, we might not be able to see all the 12 strands. The reason for that observance is that if there is a debonding length, then the tendon is not visible on the end of the span. So if the debonding length is 0, then we are able to see the tendon. Otherwise, we are not able to see the tendon in this figure. But here you can see that we have specified 5 rows of tendons, and the spacing for each row is specified here. And if you want to enter the debonding length, then we can simply go to the detailed tab. And here you can see that we have specified the jacking stress for each tendon. We have specified the bonding in the start and debonding in the end. So we have specified the debonding length. So specification of debonding length is very easy. We just have to provide the information in the form of a table, in the form of an Excel. We can just see the debonding length from our CAD drawing and we can just input it here. Therefore, we need not input all the data manually, and specifying the debonding length is as simple as writing the debonding length in an Excel sheet, and even the jacking stress is provided. If you have this data in an Excel spreadsheet, you can simply copy paste the data from Excel spreadsheet to Midas. Even that will be available. Midas is compatible with that. And simply we have specified, similarly we have specified the tendon data for the middle as well as the end span. So you can zoom in and zoom out and you can see the arrangement of the tendons. And we have specified the grouting after one stage. And if you want to see any detail, you can even refer to the details here. So what you can do is you can generate the harp tendons. You can generate the curved tendons, and this will be done automatically. You need not calculate the tendon coordinates manually and provide it to the program. So here you can see that we have specified the tendon stress, tendon data, and debonding length quite easily in just one tab. Then here we are providing the data for the loads. So here you can see that we have specified the thickness of the precast barriers, and we have specified the length of the lanes, and we have specified the intermediate median strip. And for the application of the loads, we have specified that before the composite action takes place, before the deck slab becomes a composite with the super tip girders, the program should apply the self weight, wet concrete, the weight of the wet concrete, even though the composite action has not taken place between the deck slab and between the super T girders, but still we need to apply the load due to the wet concrete, so the program will apply that. And we have specified the after composite data, that after the composite action takes place, we will apply the load due to the barrier, and we will apply the load due to the median strip, and the wearing surface data is specified. Also, the program will apply the moving load. So the vehicle load, it can be applied as per Australia and as per New Zealand standards. For vehicle loads, we just simply need to specify the lane location. So here you can see that with reference to the edge of the bridge, we can specify the lane location. So there are 4 lanes and the center of each lane is specified. So we have 4 lanes at a distance of 3.63, 7.13, 10.63 and 14.13 meters. And then we can specify the vehicles as well. So we have the Australian as well as the New Zealand vehicles. So here we will specify the vehicles as per Australia, and we will specify M1600 and S1600 vehicles. For New Zealand, we can use HO and HN vehicles, overloading and as well as the normal vehicles if we want to. So we have specified the data for the moving load, and then finally going to the construction wizard. So we are specifying the construction wizard here. You can see the 4 steps of the construction sequence. So you can see the construction sequence being modeled. We have all these 4 informations, and as soon as I will click OK, the program will start modeling the bridge and it will give me a complete FEM model. If you want, you can even save this bridge wizard. You can save this wizard as a text file and you can use it in your future models. And using this open, you can open the earlier saved wizard file. And once we have specified the data in these 5 steps, then we can just click on OK and the program will model the bridge for us. So the program will model the entire super T bridge. It will model the superstructure as well as the substructure. Along with that, the tendons will be applied, the tendon loads will be applied, the jacking stress. It will also apply the construction sequence. We will see the construction sequence in the model, and it will also apply the moving load for us. As you have seen that we already specified the moving load vehicles as well as the moving load lanes. So the program will apply the moving load. So now here you can see that we have the entire Super T bridge with us. So just for the convenience, I'm going to change the colors so that it is more convenient to see. Now this is the model, and in the next step we will see that how you can model the bridge with some different variations. If you have a skewed bridge, if you have a bridge which is skewed differently from one span to another, and if you have a bridge which is having 3 piers. So we will see some variations after this. But first of all, I will take you to the construction sequences, that what construction stages we have applied. So here the first stage is the uh, the activation of the substructure. So here you can see that we have applied the substructure, and the self weight due to the substructure is activated. Then in the second stage, we have casted the Super T sections. We have casted the Super T as well as we have casted open as well as closed Super T sections. So let us see what kind of Super T sections are activated. So here you can see that in this stage, we have casted only the Super T section. We have not activated the deck slab. So this is only the Super T section, and we have activated the diaphragm sections as well. And then in the third stage, so here if you want to see the loads, you can see that the program has also applied the tendon pre-stress load in the same stage. So we have already stressed the girders, we have already stressed the tendons, and this is the particular load that we have applied. And if I move to the third stage, you will see that the program has applied the wet load due to the slab. So the wet load is applied in the form of beam element loads. There is no slab physically yet. There is no stiffness participation of the slab. So if we see the bridge section, still it is the Super T bridge. So we have just casted the Super T bridge and we have applied the load of the wet concrete. Then in the stage 3-2, the program will actually use the transverse members, and the slab will actually be activated, and the section will now act as a composite section. Then in the fourth stage, the program will apply the load due to the barriers as well as the median strip. So that is applied here. And in the fifth stage is actually a stage for the study of the long-term effects. So the stage is around 30 years. And in this stage, we can refer to the long-term effects of creep and shrinkage. So the time-dependent effects can be studied for the long-term effects. So here we will go to the base stage again, and we will apply the moving load. So for the moving load, if you see, the program has specified 4 lanes. So at the distance that we specified, the program has applied the 4 lanes, and we have specified the vehicles M1600 and S1600. Now we will apply the vehicles to these particular lanes. For that, you can go to the load and the moving load, and we can specify the moving load cases. So we can specify two moving load cases, MVL1, where we are applying M1600 to the 4 lanes, and we can specify the MVL2 where we are specifying S1600 to these 4 lanes. So we have specified the 4 lanes and we have specified 2 vehicles, and we have applied those vehicles in the bridge. So now I will make some manipulations in the construction stage. So for the Super T bridges, since they are composite bridges in type, therefore we have specified the composite section for construction sequence. The benefit of this feature is that we can activate different parts of one composite section in various stages. So we have activated the composite section for construction stage. We have activated the composite section. We have activated the Super T section in the stage 2, and we have activated the slab of the composite section in stage 3 too. So we have specified this data here. Actually, the program has generated this data for us. And similarly, for the solid Super T, we have specified the similar data. And if you want to see, you can even see the stiffness before composite, and you can see the stiffness after composite. And similarly, we will see that there are sections which are Super T sections, but they are not composite sections. They are actually the intermediate sections. If I show you here, then you will see that the connection between the two spans, it is defined by Super T sections. They are not composite in nature. They are being activated at once. And in the next step, we will specify the activation age for the Super T girders. Let the program save the data. So here we will change the material, and let us go back to the presentation and let us review the next step before we go to the post-processing mode. So here, for your reference, I have specified the steps involved in this presentation. So we need to change the notional size of the girders and the activation age of the composite sections. And we are going to apply the temperature load in the next step. So let us review the temperature load. So here we are applying the temperature load, but before that I will change the activation age of the Super T girders. So now we will apply the temperature load. For that, we need to create the temperature load case. So we will be applying the beam section temperature. So here we have temperature load. We will create two cases, one for heating and one for cooling. And we will see that how we can specify the temperature load. So here I'm first specifying the temperature heating case, and for that the definition is quite straightforward. So we will be applying the temperature load. So here you can see that in the top 150 mm the temperature will vary from 13 degree to 3 degree, and then for the further 250 mm the temperature will vary from 3 degree to 0, and for the bottom 100 mm the temperature will vary from 2.5 to 0. So here we can specify this data. So this is the breadth of the Super T section, and we have specified H1 and H2 and T1 and T2. So this definition is quite straightforward. So I'm just adding the simple variables that what is the depth at a particular location and what is the temperature at that particular depth. And I'm almost done with the definition. So we have applied this definition to the super T girders. I will just select the super T girders and I will click on apply. Then the program will apply the temperature load. So if we want to review the temperature load, we can even review the temperature load. So I will select one particular row of the girders and we will see the temperature load here. So here you can see that we have applied this particular temperature. So we have provided the width of the girder, we have provided the height at various locations, and we have specified the temperature at those heights. So this is the temperature data that we have applied, and I will just undisplay the temperature load case. Now we have specified the entire data for the post-processing. Now we should move to the post-processing and see the results. We can see that what kind of results are available in Midas. So just for the review, we will see that what loads are available, what results are available. So here you can see that we can see the primary as well as secondary results for tendons, creep as well as shrinkage. We can see the results due to the dead load, and we can even see the summation of all those load cases. And we can see the bending moment as well as the deflection shape due to these various effects, and we can even see the stresses in the table as well as in the graphic form. So I will open an analyzed model. So here we have the similar bridge which I have already analyzed just to save the time. So here you can see that in the first stage, or let me take it to the fifth stage first. So here we will go to the results tab, and in the results tab we can go to the beam diagram. So here we will see the bending moment diagrams due to various loads. So I will switch on the legend so that I can easily see the maximum and the minimum value. So here you can see that in the legend we can see the maximum value and the bending moment diagram is available. So this bending moment is due to the dead load, and you can see the bending moments due to tendons. So this is the bending moment diagram due to the tendons due to the applied tendons, and you can see the results for the tendon primary as well as the tendon secondary. So we have all these results available with us. We have the maximum as well as the minimum values available in the legend, and similarly we can see the results for creep secondary. So here we can see the results for the creep secondary, and we can see the results for shrinkage secondary. So these results are available with us, and similarly creep primary and shrinkage primary is available with us. So now we will review the deflection shapes. So for the deflection shapes, you can go to the results and you can go to the beam diagrams. Sorry, for the deflection shapes, you should go to the deformations and deformed shape, and you can choose the load case for which you want to see the deflection shape, and I will switch on the legend, and here you can see the deflection shape of the bridge. You can see the maximum as well as the minimum deflection in the legend, and similarly due to tendon primary you can see the deflected shape. So as expected, the deflected shape for the tendon primary is like this, and similarly for creep primary we have the deflected shape, and we have the summation for the deflected shape. So we can see the maximum as well as the minimum values in the tendons. And if we want, we can see the forces as well as the deflected shape in the form of a table as well. So we can choose which load case we want to see and which stage we want to see. So the program will specify the deflection values in the form of a table, which you can easily export to Excel by clicking on Export to Excel. And then if we need to check the stresses, we can easily check the stresses from the beam stress diagram. We can choose the particular location and we can see the stress diagrams. And if you want, you can even review the tendon losses. So for the tendon losses, there are two forms of results available. The first is in the form of a graph. So if you want, you can review the tendon losses in the form of a graph. So here you can see that we can review the tendon losses in the form of a graph. We can choose the particular tendon and the stage, and the program will give us the tendon losses. And you can even review the tendon losses in the form of a table. For tendon losses, you can obtain the immediate losses, you can obtain the elastic deformation losses, and you can obtain the creep shrinkage as well as the relaxation losses for the tendons, and you can obtain the final stresses. And for the tendon loss, so the program considers the tendons based on the pre-tensioning or the post-tensioning. So we will review the results. So for example, I want to review the tendon loss for a particular group of tendons and in one particular stage. So I can just choose the tendon group as well as the stage. The program will draw a graph for me. And if you want, you can review the tendon loss in the form of a table. So you can go to the tendon loss and you can select the tendon group as well as the tendon stage, and the program will provide the tendon loss for you. So once you choose the particular stage and click on apply, the program will give you the revised tendon losses in that particular stage. So you can export this data to Excel if you wish to, and you can see the tendon losses in the form of results for the stresses as well as the forces. So both those outputs are available. And now talking about the results for the temperature load. So we can review the temperature load. So you can review the deformed shape for the temperature loads. So here you can see that we have the shape for the temperature load. And if you want, we can even review the results for the moving load analysis. For that, you can go to the results tab, and there we have various options for the results of the moving load analysis. You can see the influence line diagrams. So for the moving load, you can see the influence line diagrams. You can just click on one particular member and obtain the influence line diagram for that particular member, or you can obtain the most critical results for the moving load analysis. So here you can see that for M1600, I will just check off the load values. So here you can see that for M1600, for the element number 237, this is the location of the vehicle, and the maximum value of the bending moment can also be read from here. So the maximum moment, bending moment can also be read for that particular member. And if you wish to obtain the envelope of the moving load analysis, you can simply obtain the envelope of the moving load analysis, and the program will give you the values in the form of a table as well as in the form of graph. The concurrent reactions or the concurrent bending moment diagrams are also available for the moving load analysis. So with this discussion, we are towards the end of the presentation for this particular case. So here you can obtain some influence line diagrams, and you can obtain the critical value for a particular load case. And for the temperature load case, you can obtain the results of the bending moment as well as the deflection and the stresses. And if you wish to model the soil structure interaction, generally we do model piles and the pile caps in the model if we want to take into account the soil structure interaction. For that, Midas is capable of modeling the nonlinear soil spring supports. So here you can see that the program can model the nonlinear soil spring supports, and the program will apply the nonlinear springs. For your convenience, I have added the steps of the model generation that I followed today in one slide so that you can refer to it. So I have summarized the steps here. Okay, so now we can review the various variances of this wizard that we have used. So I will save this file and we will review that what kind of different bridges we can generate using this wizard. So we will generate a skewed bridge and we will generate a curved bridge, and we will see that how convenient it is to generate those bridges using the wizard. Let the program save this model. Meanwhile, if you have any questions, you can write down the questions in the questions window. I will be taking all the questions at the end of the presentation. Now here we will use the wizard to generate the skewed bridge first. So for example, I specify a skew support, a skew angle, and all the information is same as the previous model. And if I click OK, so you will see that the program is generating a skewed bridge for you. So you can model each and every configuration of the bridge that you wish to. Let the program generate the model. If you have any questions, you can write down the questions in the questions window. We will be taking all the questions at the end of the webinar. So here you can see that we have modeled the skewed bridge, and due to one information being mentioned correctly, the abutments are parallel. They are not parallel to the bridge, but instead they are parallel. But this is due to one wrong information in the wizard. But the idea is you can easily generate a skewed bridge. And let us say if we have 3 piers instead of 2 piers, then how do we do it? So I will go to the wizard option again, and I will open the wizard file that I've saved earlier. And for the spacing of the piers, I will change the spacing from single spacing to 2 spacings. And now the program will actually generate three piers for me at the specified spacing. So you can see that how easy it is to play with the geometry of the bridge, how easy it is to change the geometry of the bridge using this wizard. And you can generate any sort of wizard that you wish to. You can generate a curved bridge, a skewed bridge. You can change the super elevation of your bridge in a very easy manner. So here you can see that. Now our bridge is actually having 3 piers spaced at 6 meters each as I specified, and I need not change my information again and again. I can just use the wizard and modify the entire information. And if you want to, then you can also generate a curved bridge like this. So here you can see that if you want, you can even generate a curved bridge like this. So you can specify the radius of the curvature and the program will generate the curved bridge as per your specification. So now I would like to summarize the unique features of Midas Civil for Australia as well as New Zealand. This will be the last part of the presentation, and after this I will be taking the questions. I can see a couple of questions in the questions window, and if you have more questions, you can still write down the questions. So here you can see that the first unique feature for Australia and New Zealand especially is the Super T bridge wizard that we just discussed. Using this bridge wizard, it is very easy to model the creep and shrinkage. It is very easy to model the bridge geometry, incorporating the construction stage. And then the second feature that we have is the creep and shrinkage as per AS5100 Part 5, which is expected to be released in the mid of this year. So Midas Civil is supporting the creep and shrinkage models as per this code. And since New Zealand is following the creep and shrinkage model in AS5100 Part 5 with some changes, so I would like to mention that you can even incorporate those changes as per the New Zealand Bridge Manual, and you can simulate the creep and shrinkage. You can simulate the time dependent effects as per New Zealand. And then, as I mentioned, we have the database of Super T girders varying from 750 mm to 1800 mm depth. And we are now organizing a web series for the bridge design. So we will be covering Super T bridges, plank bridges, segmentally constructed bridges, and we will be explaining their modeling process. So it will be helpful for learning on how to use the software. And the program is supporting the displacement based seismic design. So the new version of the code will be following two approaches for the seismic design. One will be the displacement based and the second one will be the force based. The code is giving an option between these two approaches of the seismic design. So Midas Civil is capable of performing both the approaches. So these are the unique features in Midas Civil, which will be helpful for the engineers in Australia and New Zealand. Now, while registering for the webinars, we had a section for asking the question and answers. There were three questions in the registration that were very common. So I thought that I should answer all those questions here in the webinar itself. The first common question was regarding the HO and HN vehicles as per the New Zealand Bridge Design Manual. So the users were asking if we can simulate HO and HN vehicles as per the New Zealand. So here I would demonstrate that how you can simulate the HO and HN vehicles as per the New Zealand Bridge Design Manual. So here I will show that how you can easily generate the HO and HN vehicles. So let us say in this model we have we haven't specified the moving load data yet, but we can easily specify the moving load data using the graphic as well as using this script. So we have both the options. We can use the script and we can use the graphic interface as well. So here I have used the script and here you can see that we can use the HO and HN vehicles. So this is the lane load. So here you can see that we have specified the lane load of 3.5 kilonewton per meter square. Since the width of each lane is fixed to 3 meters, so the lane load becomes 10.5 kilonewton per meter, and there are two truckloads of 120 kilonewton each. So this is the HN vehicle, which is the normal as per New Zealand standards. And then the second we have is the overload, which is 240 kilonewtons spaced at 5 meters, and the lane load is 10.5 kilonewton per meter. And when we are going to generate the moving load cases, then we can specify the multiple presence factor. Since the New Zealand bridge design manuals specifies the multiple presence factor, so we can simulate the multiple presence factors as per the bridge manual, and we can easily generate the HU and HN vehicles as per the New Zealand standards. The second common question was the creep and shrinkage models as per the Australian standards. So here I would like to mention that for the creep and shrinkage, as I've already demonstrated, that the creep shrinkage model is available as per AS5100 part 5. So the equations have been changed. They have been updated to the new standard, which is expected to release in the mid of this year. And if you want to use AS3600, then you can even use AS3600. Essentially, the creep and shrinkage model of the new code is based on AS3600. You can find quite a lot of similarities between the two models. So the program incorporates AS3600 creep and shrinkage model as well. Then the question was regarding the users of Midas Civil in Australia and New Zealand. For that, I will be demonstrating from one PDF file that what are the users of Midas Civil in Australia and New Zealand. So in Australia and New Zealand, the users of Midas Civil include WSP Parsons Brinkerhoff, Arup, Arcadis, SMEC, MWH Global, AECOM, Becca, Jacobs SKM, and Eurecon and Hyder. So these are some of the users of Midas Civil in Australia and New Zealand, and the program has already been used for quite a lot of examples, quite a lot of project applications. And thank you for joining today's webinars. If you have any question, you can write down the questions in the questions window. I will be taking the questions in a while.